Yes, Shashi Kumar. You can text me what do you want to discuss. Put it in the chat box. Yes, Shashi Kumar, just put it in the chat box. What do you want to discuss? Am I audible? Okay, thank you, Akshay. Yes, man. People, whoever have raised their hands, they can put their query in the chat box. Okay, whatever they want to tell. Or Mr. Shashi Kumar, you can just unmute yourself and tell what do you want to discuss. Or the next person is Mr. Bharat Kumar. Oh, okay. Then why don't you just put it in the chat? Oh, okay, okay. That's why you raised your hand. Okay. Oh, okay, okay. Okay, I thought you had some technical doubt. Okay, Shashi Kumar. Probably, I think I need to change the settings. That's all. Okay, and what about Bharat Kumar? What was your query? Okay. Okay, I mean, I'll just continue. I'll just start the lecture or summary. Meanwhile, whoever have any doubts or queries you want me to explain any topic, you can just put it in the chat box. Okay, that's fine. So yeah, I welcome all of you to the sixth tutorial session. So what are we going to do today is, I'll just briefly summarize whatever professor has been discussing, and then we'll solve some tutorial problems. And today we'll start with one of the question which your friends have asked me. Why don't we simulate an air separation plant? Okay. So today we are going to start the simulation of an air separation plant. Okay. So I'm expecting all of you to have Aspen with you. So just to confirm, do you have an active Aspen with you now? Can you use it? Can we do a problem? Can we do a simulation over here? Yes. Okay. Others, can you please confirm that you have an active Aspen with you now and you can do some simulation along with me? Two, two candidates, others? Depending on your confirmation, I'll have to plan the lecture, right? So if you can confirm that you can use Aspen now, we'll pick up a problem statement on air separation plant and then we'll try to simulate it. Okay. Okay. So just before going to that problem, please switch on your Aspen, keep it ready. Okay, it will take some time to open and get all set. Meanwhile, I have few small questions. Okay, but this will cover your technical stuff, whatever professor thought this will. Okay, so yes, so in this week, professor was discussing about different. Basically, was giving different predictions based on different models. Says calculates azeotropic points for different compositions that are been given, and then he says he also developed PT envelopes, etc. All right. Then in the PT envelope, one of the lectures I was studying that the standard method will fail in some of the regions, whereas the density matching method, which is actually a product from our lab, has a better prediction than the standard one which Aspen uses. You can clearly see that for the given composition which professor was trying to explain, you can see that the standard method which Aspen uses fails in the critical temperature and pressure region. However, the density matching method, you can see that we are able to get the two-phase critical point very correctly, and there is no failure in this case. Okay, just want to show you this result. Then later on he was discussing about real systems. Basically he took one example of nitroethane and cyclohexane. He calculated activity coefficient using different models, right? Then later he explained about model analysis tools which are available, basically the sensitivity analysis, design spec, which we have actually used during last exercise. Then optimization, both constraint and unconstrained. Then regression tool. So today's class, what are we going to do is the parts of this. Okay, we'll do an exercise on sensitivity analysis, we'll do an exercise on design spec. In further coming lectures we'll do an exercise on optimization. Okay, putting all together, we can't be done in 1 hour. Okay, so we'll start step by step. All three of this we'll be doing hands-on experience. Okay, we'll get to it. Okay, so meanwhile going to Aspen, I just have few questions for you. Okay, so the change questions is the change of pressure, so it really helps in the separation of water, acetonitrile, azeotrope through distillation. Is it true or false? So these questions are made from lectures. Okay, so this gives me a guarantee that people are following lectures and are able to understand it. Okay, so I'm just having let's put a poll for this. Can you please respond? So it says water and acetonitrile would form azeotrope. So can we change the pressure of this system and do a distillation? Okay, only 2 votes. Others? So to extend this question, what kind of azeotropes do we have? How many varieties of azeotropes do we have? Anyone? Can you please respond? How many kinds of azeotropes do we have? And what are they? You can just guess the answer. It need not be correct. Okay. Okay, see, essentially we have two kinds of azeotropes. Okay, homogeneous azeotrope and heterogeneous azeotrope. Okay, so what happens in case of heterogeneous azeotrope is you will be able to see two layers of liquids. So using a decanter and the distillation columns, you'll be able to separate it. However, when your system forms an homogeneous azeotrope, what is conventionally followed is change the pressures. We have two distillation columns which operate at different pressures. So this azeotrope composition is also a function of pressure. Okay, so using that, you can see that this particular system forms azeotrope at this composition at, at, at one of the pressure. However, when you decrease the pressure, you can see that the azeotropic point shifts to here, and further reduction in pressure brings your azeotropic point over here. So what is done is, in one of the distillation columns, say let us take an example that I have one column operating in this region, another column operating in this region. Okay, so one of my product will be pure water, and one of the product from the column will be water, and another product will be azeotrope with this composition. Now if I send to second column, what happens is one of my so I'm taking this composition, right, from point 3, I'm taking it to second column. So the second column my products will be uh, whatever the acetonitrile over here and this particular azeotrope. Okay, so now what I'll do, I'll then bring it down to this pressure, then I'll be able to separate water from this, and again I'll get this. So basically I'm having a loop. So two distillation columns operating at two different pressures will be in a loop to separate these two pure, separate the mixture into two pure components. Okay, so this is how the homogeneous azeotrope separation is carried out. Did you understand how it is carried out? Could you follow how the homogeneous azeotrope distillation is carried out? Or do you want me to explain again? I'll give you an example of heterogeneous azeotrope, but just before that, I want to know whether you could follow how a homogeneous distillation is done, homogeneous azeotropic distillation is done. If you don't respond, by default I'll understand. I'll think that you have understood it. Okay, I'll continue with whatever I had planned for. So do respond if in case you didn't follow. Okay, fine. I'm assuming that all of you have understood how the homogeneous azeotropes are separated using distillation. In this question itself, further questions, we have one of the example of heterogeneous azeotrope. That time we'll discuss more about it. Okay. So yes, we'll see one more question. So given an ideal system, what would be the activity coefficient of it? I'll just put a poll for it. This now given ideal system, so what would be the activity coefficient? Is it less than 1, equal to 1, or greater than 1? See, I get only 2 votes. Given the first question, I had only 2. Yes, 2 of them are responding. Why? This seems the question to be very silly, is it? That's why you don't want to respond. Is that what you mean? Okay, fine. Anyways. So, for activity for ideal system, it's equal to 1. For example, now the example which professor was taking was, he took nitroethane and cycloheptane, right? So when he was using NRTL, which I discussed, or you see, in this case, when he was using NRTL method, so he was getting activity, better prediction of activity coefficient, which is less than 1 in most of the regions. Then when I put an ideal equation of state for calculating activity coefficient, what I get is the value becomes 1. Okay, so for any ideal system, the activity coefficient is taken to be 1. Okay, fine. So here is one more question. So what are the valid phases for nitroethane and cycloheptane ethanol mixture at standard temperature and pressure conditions? So how do we actually know what valid phases should we select for the given mixture? I'll just discuss the theory behind it after this question. So please do respond. Just end this for that. Yeah. So given the mixture of 3 components, I'm saying how do we identify the valid phases? Or in this case, the question is asked, what are the valid phases for this given mixture? This example is actually taken from professor's lecture, so that's actually the reason why it's directly asked over here. Okay. So if you had followed the lectures, then you should be able to answer this question. Okay, I have 4 votes. I'm happy yet. Last time I had 3 and now 4. Some improvement. Okay, see, the first duty for us to find out whether the system, given system, it could be it's obviously a mixture, we are talking of a mixture. So for the given mixture, we should verify whether it forms azeotrope or not. Okay, then we need to see its state at various temperature and pressure conditions. Okay, after looking that, we'll be using non-ideal equations, obviously, such as NRTL or Penck-Robinson, whatever suits to your mixture setup. Okay, so based on that model, we'll try predicting whether it forms as eutroph or whether it forms VLLE, it shows VLE in the temperature and pressure regions. So all those things we'll verify, and after verifying this in the property analysis tool, then we go to simulation. Okay, so once after doing this property analysis, we'll know what are the valid phases for the given setup. Okay, so then in the simulations, we can accordingly define what are the valid phases in our existing system. Okay, so that's how we do. So in this case, it's VLN, right, because they form azeotrope. Okay, so it's actually a heterogeneous azeotrope in this case. So we'll say the valid phases are VLN. Okay, this actually example is taken from professor's lecture, so it's not further explanation will not be required actually. Okay, fine. So yes, so here is one more question. The ternary mixture of nitrogen, oxygen, argon can be separated through cryogenic distillation. Is it true or false? And even before this, I want to ask you, what is cryogenic distillation and how is it different from a conventional distillation? Can you please respond to that? Just put that answer in the chat box. Okay, whatever you have idea on the cryogenic distillation. Okay, what is difference between a cryogenic distillation and a crude oil distillation? Just that should be fine. That should give me the answer. How is cryogenic distillation different from crude oil separation process? Okay, distillation below 0 degrees. Thanks for your answer. Any other student would like to respond to this? See, it may not be correct. Okay, just give me an answer. That's fine. Okay, -1 degree. Okay, any other answers? So one says below 0 and another says -1. Both are in degree centigrade. Any other responses? Process of separation of gas mixture using simple distillation of high pressure and low temperature. High pressure and low temperature. Okay, so high pressure, can you just define your high pressure range? Of what range you're talking of? Low temperature means okay, below 0 degrees, that I could follow. High pressure means say 100 bar, 200 bar. About what range you're talking? Okay, no issues. And thanks for your response. At least you are responding, others are not even responding. Fine. So bring the air below critical temperature. Wow. Okay. So what is critical temperature of air? So you mean if I bring any component, no, if I bring temperature below its critical point, then it's called cryogenic distillation. Is that what you mean? Uh, yes, I'll just take it over. Okay, and thanks for your responses. So essentially, for the students who are working in refrigeration system, they'll be very much fascinated about these things and all. Okay, so the temperature ranges are divided into four categories. Okay, uh, the baseline lays above and below ambient. Okay, that's the baseline. So below ambient, there are two regions. Okay, so if I'm assuming ambient to be 300 Kelvin, okay, approximately, it's not, at least in Chennai, it's about 40 degrees centigrade. So, however, let us assume the ambient to be 300 Kelvin, okay. So, if I assume ambient at 300 Kelvin, then any temperature above 123 Kelvin comes under refrigeration temperature, okay, above 123 Kelvin. And the temperatures below 123 Kelvin are called a cryogenic temperature range, okay. So we are talking of temperatures below 123 Kelvin. Okay, so I talk everything in terms of Kelvin so that there is no confusion of this minus 30, minus 100, minus 50. No, it's quite confusing when we talk of positive and negative numbers together. So let's keep everything positive. Okay, so the temperature which is below 123 Kelvin is known as cryogenic temperature. Okay, so what happens in cryogenic distillation is uh, basically like nitrogen has a saturation temperature of 77 Kelvin at 1 atmosphere. Okay, since it is having 77 Kelvin, if our aim is to produce liquid nitrogen, then obviously we need to go further down, right? Further below 123 Kelvin. So that's why it's called cryogenic distillation. It's the same fractionating column, same simple distillation. However, since it is operated below 123 Kelvin, it's called cryogenic distillation. Okay, that's the only difference between a simple distillation, like an example of crude oil distillation, and cryogenic distillation. Except the temperature ranges which we are talking of, everything else will remain same. Okay, so in this case, yes, since nitrogen has 77 Kelvin and the others have about 86, 96 Kelvin, so all the three, whatever we have asked in this question, have the saturation temperatures of less than 123 Kelvin. Okay, thus it requires cryogenic distillation process to produce and separate them and to liquefy. Okay, so what I'm doing is go back here. So could you understand what I told? The definition of cryogenic temperatures. Okay, let me end this. Okay, fine. So yeah, this is one of the setup of air separation plant, which will simulate. Okay, we will be starting this flow sheet simulation today. However, it will take really good time to finish it off. So what is done is purified air is compressed in multi-stage compression system. It's pre-cooled absorptions. Absorption is used to remove the impurities. Okay, two types of sieving materials are used: molecular sieves, activated alumina. Okay, two of them are used. Then we have booster air compressors. Finally, we have main cooling heat exchangers, which is their cold box when you go to an industry. Then we have an expansion turbine. Finally, all this go into a double column distillation setup. Okay, we'll set up this flow sheet. Okay, there I'll explain the entire process in more detail. Okay, see, I have actually worked in air separation plant. Okay, so I know quite details of what happens over there. So we'll work on it really good. Okay. Anyway, so just come back to the simulation. I have couple more questions. Okay, so water and trichloroethane forms an immiscible homogeneous binary mixture. Is it true or false? Just black hole. Yes. The question is water and trichloroethane forms miscible homogeneous binary mixture. Is it true or false? Only 4 outs. Again, it has come down, is it? So the previous question I had 5 outs. Where is that one more person missing? Oh yeah, I have the fifth quote. Thank you. Okay, see, uh, few minutes ago, one student was asking, give me an example of heterogeneous azeotrope. Okay, so this actually forms heterogeneous azeotrope. Okay, water and trichloroethane. So it's actually the answer is false. No, it forms a heterogeneous azeotrope. Okay, so the shape of this curve, the TXY diagram for an heterogeneous azeotrope will be of this sort. However, the homogeneous azeotrope, which I have shown you previously, will be of this sort. Okay, so you can see that you have only basically you'll have the curvature throughout the profile and the intersection point will be at one area. However, when you have an heterogeneous azeotrope, you'll have a horizontal line. Okay, just a horizontal line, and then you have the two curves. Okay, so that's how you can differentiate between a homogeneous and heterogeneous azeotrope. Okay, fine. So yes, I have one more question. It says that the two components I have AW and AM, and this is Gibbs energy. Okay, this is plotted Gibbs energy, and on the x-axis I have mole fraction of component A and B. Okay, so you just observe this plot. Okay, it's a parabola, right? It's a parabola. On x-axis we have mole fraction of component 1, if I am correct. No, it's component 2, and then on y-axis we have Gibbs free energy of mixing. Okay, now the question is the mixing of component A and B, is it spontaneous process or no? That's the question. Okay, can you please respond for this? How do we I know after once you answer, I'll explain how do we distinguish between spontaneous and non spontaneous process from this plot. So it is a parabola. Okay, on y-axis I have Gibbs free energy of mixing, and then on x-axis I have mole fraction of one of the component. Okay, so after seeing this plot, can we decide that is it a spontaneous process or non-spontaneous process? How do we distinguish between two? Okay, people who have answered, can you please comment in the chat box? How did you say that it's a spontaneous process? Do you have any reason why you commented saying that it's a spontaneous process? Anyone? Three students, whoever have responded. No, you can be wrong. Okay, just tell me your idea. We are here to learn, right? So nothing wrong in saying an incorrect answer. Okay, see, essentially in nature, mixing or separation, whatever happens, is based on Gibbs energy minimization. Okay, if we observe that the Gibbs energy of individual components is higher than that of mixing, then they exist. They prefer existing in a mixed form. So here we can see that when mole fraction of one of the component becomes 0, we have Gibbs energy of 0. Another one is also very high. However, when we mix both of them and all their composition, you can see that it has a lower Gibbs free energy than the individual components. Okay, thus the mixing is spontaneous process. Okay, so that's how we separate between spontaneous and non-spontaneous process. Okay, fine. Now, what are we going to do is, I have one more question. That's already the second one. Okay, so what I want you to do is, see, we'll basically do simulation of this process. However, we'll divide into three sections. Okay, so we'll say we'll simulate this heat exchanger in one session. We'll simulate the cold end of this section process in another section, and simulate the distillation itself in another section. Okay, so at complete we have 3 sections. So once after finishing these 3 sections, what all we learn very properly, one is design, using design spec, then using sensitivity analysis, then how to use calculator block in Aspen, and how to use optimization tool available in Aspen. Okay, this 4 is our agenda doing the air separation plant in 3 segments. Okay, so if you yeah, someone commented something. Yes, Bharat Kumar, you can just comment whatever you want to discuss. Okay? Just put it in chat box. So what are we going to see? If you observe here, the liquefaction process, whatever we have over here is presented in simple terms. So we have compressor, after cooler, then we have heat exchangers, right? So from this is the main heat exchanger which we have separated. Okay? So from between the main heat exchanger, okay, from between we take one of we takes a part of the compressed feed and expand it and send it to the other. So that's what happens in any air separation plant. Okay, so this is called Kapitza liquefaction process. Okay, to be technical. So now our basic idea is to simulate this particular cold end section of the column. Okay, so this is our first task. Okay, so what I want you to do is just set up this small flow sheet. Okay, so I have a turbine, a two-phase turbine, and I have a phase separator. Okay, instead of air we'll start with nitrogen. Okay, to be simple, starting we'll take nitrogen. Once we set up the distillation column, we'll go with air. Okay, so the liquid air yield, no, sorry, not air, this is liquid nitrogen yield, is defined as the nitrogen that is liquefied to that which is compressed. So in this flow sheet it is essentially M7 by M5. Okay, now I want you to find out the temperature of 5 for various pressures. Okay, 5 bar, 10 bar, 50 bar, to obtain yield of 0.6 and 0.7 given the outlet pressure of cryoturbine. The turbine whatever we are talking of is 1 bar. Can you set up this flow sheet? Meanwhile, Bharat Kumar, you had something to discuss, right? Others, just take a screenshot of this question and keep the flow sheet ready. Could you understand the question? This should be the first question to be asked. Could you follow what I asked you to do? Or shall I repeat the question? See, if none of you respond, by default I'll understand and I'll think that you understood everything. Anyways, thanks. Please repeat the question. Okay, thank you, Mr. Sashi Kumar and Akshay. I understood. Okay, so we'll start with very simple thing. Okay, we'll simulate only 2 units for now. Okay, we have one turbine and one phase separator, two-phase separator. Okay, so now I am saying I have nitrogen feed. We are not even considering air. It's just nitrogen. Okay, nitrogen, it is coming at some temperature which we need to find out. Okay, however we know the pressure, says 5 bar in one case and 10 bar in another case. So we have 2 cases to be solved. So first let us take the first one. So we are saying the pressure of stream 5 is 5 bar and temperature is unknown. However, let's say we'll start with 120 or 130 Kelvin. Okay, we'll just start it. So okay, so the and flow rate, let's say it's 1 kg per second of nitrogen. Okay, now this is expanded to 1 bar. Okay, I have P6 to be 1 bar, and through a turbine, since it operates below 123 Kelvin, it is called cryoturbine. Okay, so cryoturbine has an isentropic efficiency of 70%. And in the phase separator, the idea of phase separator is to separate the gaseous phase and liquid phase. Okay, the liquid nitrogen is collected from below and the vapor part is taken from the top. Given we have a definition of liquid yield, which is the ratio of M7 by M5. Okay, now I want you to find out what should be the inlet temperature of nitrogen so that we have a yield of 0.6. Okay, that is the question. So this can be done using either sensitivity analysis or design spec. So I want you to do with both of them. Okay. Is it clear now? Could you follow? Shashikumar and Akshay, could you follow? Okay, great. Can you just set up the flow sheet in case if you are confident that you understood the problem? And let me know where are you facing the trouble. Okay. Others, do you have access to Aspen now or no? Akshay has. Anchal, do you have access? No, okay. You don't have the software now, Shashi Kumar. Okay. Akshay, do you have the Aspen now? Yes, okay. Then can you do that? So only one of us has, is it? None of the other student have? So from next class, can you keep the things ready? Will you be able to have Aspen with you during our interactive session? Okay, thank you, Sashi, so much. See, the aim of this live interactive session is to, tell you, guide you in whatever area you are having difficulty. Okay, so with Aspen Plus, things will go just like beautiful song when things are just going like that. But uh, the idea is to know what do we do when we get errors. Okay, so without you doing it yourself, you won't be able to identify the errors which you get. Okay, so if I just set up a flow sheet and show you the solution, that's fine. I mean, it's just a repeating part for me, but you won't be able to learn much out of it. So when you do with your hand, then you'll be able to learn a lot. Okay, that's the basic idea. You know, which model pellet for turbine? So it's the compressor. Okay. Say once you go to simulation, okay, let me see if I actually taken the components. So the first idea is to give the components. Okay, so nitrogen. Okay. Now the second thing is to specify the method. Okay, also Peng Robinson. That's where it's given. If two things are done, now we'll go to simulation. Okay. See, I'm not showing the entire thing now. Okay. Just tell you the basic funda, but it will be good if you can do it. So for turbine module, just go to pressure changes, select the compressor one. Okay. In Aspen, we have the same model pellet for compressor as well as turbine. However, in HYSYS, you'll have two different ones. Okay. Then for flash separator, you have the separator over here, right? Under the tab, you have flash 2. So use that. Okay. That's all. So I have some inlet stream coming here. Have some outlet stream going here. I have vapor going back. Liquid coming down. Right? That's all. This is what I have asked you to do. Okay. So once the flow sheet is done, okay, let me ask the person who is doing it. Akshay, could you set up the flow sheet, whatever I have shown you on the screen? Yes, okay, so the flow sheet is done. That's great. I'll come after you, okay? You just tell me your status. Whatever you have completed, I'll keep on doing. I don't want to go before you. I'll go behind you, okay? Just put a message on the chat box once you finished giving the required inputs. Okay. So the next part is to give inputs, right? So now we said we'll give some random temperature. We'll start to say 120 Kelvin. Okay. Pressure which we gave us 5 bar, right? Same one. The component which we are talking of, nitrogen, right? Same nitrogen. Okay. The other thing which we said is this is turbine, right? Isentropic. Outlet pressure is 1 bar. We said the efficiency is 70%, right? Another thing which we need to give is, since we are talking of a two-phase separation, then we should change the convergence. See here the default, it says only vapor. We need to change this to vapor liquid, okay? Since we are now solving a two-phase problem. That's one more thing which we need to take care. Then we said for fast separator, let's say there is no heat duty and there is no pressure. That's all. These are the two inputs required for flash separator. Now you can see that it says the required input is complete. Okay. Just save this and let's run it. Let's see what happens. Just see, it says it has got some results. Let us see. Right. You can see that the flow rate of the stream 4 is 0. Okay. Basically the inlet temperature whatever I gave is not that really great. Okay. So we'll say some 90 Kelvin and let us set. Let's see. Okay, it says warnings. The warnings. Now if you I know what warning it will give, but we'll see. Basically it will say that it's two-phase entry. That's what. See, feed is below the dew point. Okay, that's what it says. So now if we see, the stream 4 has a flow rate of 87 and the rest is going to stream 3. So in this case we are able to liquefy 87% of the nitrogen which we are sending to it. But however, our idea, the question which is asked is to have 60%. So our aim is to make this 4 as 60%. Okay, it's 87 now. So we need to find temperature of inlet such that my outlet flow rate is 60%. Okay. What we'll do is, first I said, what are we going to learn? We said we are learning 4 things. One is the calculator clock, one is design spec, one is sensitivity analysis, and another one is optimization. So now we'll see the design spec. Okay. So go to design spec, a new one. Okay. We'll say we'll define it. Okay. It's stream 4. Okay. Stream 4. So this is string variable 4 smaller flow. Okay. Specify N4. I want N4 value to be 60%, right? I'll say I can able to tolerate up till this much. What should I vary? The inlet stream temperature, right? Stream 1 temperature is the key. So I'll say the limits to be 80 and 120. Okay. Let us see whether it will give us result or not. Oh, it says error. What is that error? So when unless you do this all these things, you won't be able to see what error you are getting. Okay, so that's why I asked if you actually have Aspen with you or not, but most of you don't have, so that's why I started doing. So yes, can anyone tell me what was the error I had? What is the reason? See, it says it see it didn't converge in 30 iterations. Normally in the final pass, basically it didn't converge, right? So what do we do now? We'll say go to options, default method. We can see that for design spec we have secant method. We'll change the secant method to Newton method. Okay, and I'll go to methods. I'll increase number of iterations for Newton method. Okay, then let us see whether it will run or not. So even now if it doesn't run, we'll try to find out why it is not running. Again we have got some error. So let us see. Now the other question can be, is it actually possible to do this? So to answer that question, what we can do is do a sensitivity analysis. Okay. So we'll deactivate the design spec and switch to sensitivity. Okay. We'll say vary the inlet temperature and find the outlet flow rate. Okay. Temperature. So my starting point is 80 Kelvin and ending point is 120 Kelvin. An increment of 1 Kelvin. Okay, so for every 1 Kelvin increase, we are trying to calculate this. Now, we want N4, right? N4 stream variable, stream 4, talking of mole flow, fill variables. Let us see how the outlet flow rate varies. See here you can see that there's a sudden jump from 84 to 6%. So essentially what are we talking is, for the given conditions, it's impossible to find a temperature. Okay, so unless we do a sensitivity analysis, we won't be able to understand why the design spec was giving us an error. Okay, this is the reason why the design spec was giving us an error. Okay, here you can see that there's a sudden jump from 84% to 6%. Okay, so that's the reason why the design spec fails. So what can we do? We'll do this. Okay, we'll change the operating pressure. We said it's 5 bar, right? The second question we had 20 bar. Okay, now let us see what happens to 20 bar case. Yeah, in 20 bar you can see that there is some of at least somehow there's some linear increase from 60 to 90%, right? However, from 17 to 60% there's a sudden jump. Okay, so we should see why it is happening. So can anyone explain why there is a big jump? uh, Installation procedure is it's out of my jurisdiction. Okay, I'm here to give guidance on the technical aspects of it, but not the installation procedure. You can just mail to the concerned person. Sorry. So can anyone explain why I have a sudden jump over here? Okay, see, we are talking of pure component, right? So when you plot a TH plot of nitrogen, okay, what you observe is uh, when I'm expanding. Okay, let me just. Okay, I'm using a different software to make it bit simple. This is RefPro. Okay, so yeah, it says nitrogen. I'll show you. I'll just explain why it is happening. Okay, so I want a TH plot. Okay, I want 1 bar. I want 21 bar. Okay, fine, this is fine. Find the saturation points. Okay, see, uh, we are saying in one case we are cooling it down. See, you are able to follow the pressures, right? So this is 6 bar, however I'm assuming to be similar to 5 bar. Okay, so in one case we are saying we are cooling it down to 100 Kelvin and then expanding it, right? So when you expand from 5 bar to 1 bar, you can see that you have some fraction of liquid. However, just increase of 1 Kelvin from here till here, you are completely into saturated vapor region. So when you are expanding from saturated vapor region, whatever liquid product you are getting is just zero. Okay, so that's how there is a sudden jump. So since we are talking of a pure component, you'll have one, at every pressure you have a fixed temperature, okay, saturation temperature. Okay, so if you expand it below that temperature, you'll have more of liquid. So that's what we could see over here. When we expanded it from 80 Kelvin to about 100 Kelvin, we could get some fraction of liquid, about 90%, 80%, 70, 60 and all. However, with just slight increase in temperature, we are in this region. Okay, so when we expand from this region, all we have is the superheated vapor and the liquid phase becomes almost zero. So that's why we have a sudden shift in that calculated value. Okay, fine. So could you understand why there is a sudden shift? Yeah, that's great session, Kumar. Thanks. Okay, so could you follow what I did in sensitivity and design spec? So will you be able to finish this assignment before coming for the next week class? So I had actually planned for one more thing today, but we won't be able to finish. We'll start from here the next week lecture. Okay, so what are we going to do is simulate this liquefaction process. Okay, then further go ahead with the complete process whatever we talked. Okay, so essentially we have two distillation columns and the cooling part. Okay, so as of now we just started this section of the column, okay, the lower end. In the coming lecture, in the coming class, we'll simulate this section of the process, and we'll try starting the distillation aspect as well, and together we'll put them, and finally we'll simulate the entire plant. Okay, so that's how the plan for the next week lecture is. So do you have anything else to discuss? You want me to discuss any more? You have any questions in today's class? Okay, thank you, Sashi Kumar. Yes, ma'am.
So can you just do that? There's a cryogenic one. The problem was there. Can you display that again?
Yeah, sure, I'll do that. Yes. This one?
No, the previous one.
This one?
No, this cryogenic.
I mean, whatever we are doing is the cryogenic separation process, so it's all together.
Okay. Okay. No, I was unable to. I didn't get the link actually. I got it late.
Okay, fine. See, ma'am, the basic idea of this session or the next coming session is to simulate an air separation plant. Okay, so some of the students were asking why don't we simulate an air suppression plant? Okay, so taking that as an idea, I said, okay, let us start with one of the section of the air suppression plant today, then slowly we'll finish off this flow sheet. Okay, so we started with the cold section of the plant, then I said, then next week we'll discuss, we'll simulate this heat exchanger part and the distillation part as well. So once we put all of them together, we'll have an air suppression plant, the simulation. Okay, so that's the basic idea.
So I don't have anybody's number. Can anyone share so that I can have the I have downloaded the software, but I'm unable to install it. So can I get anybody else's help?
Ma'am, just send a mail to Professor, okay? He has a manual for installation, Professor Pratikar Kumar Saha. So he might just share that with you. So anything else? Okay, anything else? So if if you have nothing to discuss, then yeah, which discuss. No, I didn't get your question, Mr. Maul. Can you please expand your question? I couldn't understand. Is this related to Aspen or you are asking something else? Okay, you're asking about Java. Okay, let me just stop the recording. Give me a second.